Hi, welcome to YouTube Shorts by Kumaresan at Geetham. This is perhaps the third one. Today we are going to talk about how to understand cosets. We will concentrate on cosets of subgroups in a group, but whatever I say will carry over to linear algebra, ring theory, module theory, everywhere. But you just have to get the hang of it. That's all our plan is. Okay, so let's try to keep it quick. Yeah. So suppose I have a subgroup H of a group G. Okay, then a left coset R of the form AH, where is A an element H, A is an element G. Right? Now two things. How to look at a left coset. Two, when you study quotient structures, quotient groups or quotient rings, quotient vector space, quotient modules, etc., you have to look at the set of left cosets. Right? How to look at them? These are the two things I want to talk about today. Okay, let us look at simplest case to start with. See, all my examples are geometric, therefore my groups need not be finite. So let us look at G equal to R2 with under addition. As a subgroup H, let us take the y-axis. What does that mean? That means x equal to 0. Set of all 0, y is in R. Right? Now suppose to start with an element here, P, let us say call it A, B, then AB plus H, this is a left coset, this is P plus H, this is a left coset. That is the form you can see that it's A, B plus Y as Y varies over R. This is same as saying AY and Y varies over R. Right? They call this as Y dash, they can always solve it as Y varies over R, Y dash varies over all R. Therefore I can solve for this if you do. Okay? So what is this? This is sec x equal to A line, vertical line parallel to the x-axis, to the y-axis. So this is my A, B, then this is this line. This is my A, call it P plus H. Okay, this may be this is my point P. Do you understand that? So any coset of H is a vertical line parallel to y-axis, and therefore set of cosets, that's a quotient set. It's actually a group, I don't want to look at that now. It's a quotient set. This is nothing other than all a line in R2 parallel to y-axis. Right? So these are the things. So let me just do that. Let me also see whether I can do straight line. So these are the cosets. So now you can see, you can also now understand geometrically why given any two cosets, okay, either they don't have any point in common or they are identical. If at all they intersect, they have to be identical. Alright, because when are two lines parallel, either they are identical or they are completely disjoint. Yeah, you know from geometry, that is the interpretation. Right? Let us look at one or two more examples before we go further. Let us look at example 2. Okay, now my group G is C star under multiplication. This is all non-zero complex numbers, right? So think of this as this. So this point is removed. This point is removed, right? Now as a subgroup, okay, I am going to start with H equal to all complex numbers in G, that is C star, so that modulus of z equal to 1. Right? Now what do I want to understand? I have to add a next line, right? Yeah. So I want to understand, suppose A is a point C star, then I want to look at AH. Now AH is going to be A times Z, where Z is in H. But remember, A times modulus A times Z is same as mod A. Alright? Therefore, start with any point. Please understand, go slow. Suppose W is a point AH, then W is of the point A times Z. Therefore, mod W equal to mod A. Right? So, all elements, okay, for every W in AH, I have mod W same as mod A. Conversely, if you give me a W in C star, so that mod W equal to mod A, okay, then let us define Z equal to W by A, then mod Z will be 1. Therefore, I can write W equal to A times Z. So, what I have shown now? Therefore, I have shown this is, now I have a geometric description. This is set of all W in C star, so that mod W is same as mod A. Right? Now, what is the geometric interpretation? Geometric interpretation is this. So, remove this point. This may be my A. Right? Therefore, what I have is, okay, this circle. Okay, all things. This is mod A. Radius, this. The picture is not good. Okay, it doesn't look like a circle, but you understand this. Therefore, this is circle of radius, mod A, center at origin. Remember, origin is not a point of G. Okay, this is just for us to understand geometrically. Yeah. Therefore, so any coset is a circle of radius r positive with the center at origin. Now, what is the set of cosets? Now you can see these are all parallel lines. So these are the cosets. So cosets are set of parallel or what they want to say, parallel circles. One usually say concentric circles. So you can see that is, again, the geometry is very clear. Okay, how do I understand? Given two cosets, either they are their intersection is empty or they are identical. If they have a point in common, they are the same. That's because parallel things. So you can see the set of cosets are class of parallel objects intuitively. Okay, let us start with one third example. With that I will stop. I will give an exercise. Same as C star now, but H is R plus. That is, I'll set X in C, so that X is in C star, X is in R, and X is positive, all positive reals under it. So this H is a subgroup. H is a subgroup of G, multiplicity subgroup. So identify the cosets and then class of or set of cosets. Okay, you will again find what do you mean by parallel here. Okay, this, remember, these points are not, this point is not there, so they will be essentially lines like this. Okay, semi lines, but I leave it to you. The fourth example, yeah. So now let us look at the last example. My G is GL2R, 2 by 2, 2 cross 2 invertible matrices. Okay, and this is same as saying determinant of A is non-zero, not equal to 0 if A is in GL2R. Right? Now let's look at H to be the subgroup ASL2R. Right? This is, okay, this set of all A in G, so that determinant of A is 1. Okay, one usually call it unimodular matrices. Okay, now suppose I start with an element A. Unfortunately, I will use the same capital letter. I hope it doesn't cause any confusion. A in G, what is the left coset AH? Okay, right? So this AH consists of all A times B, where B is in SL2R. Right? Now notice that if my C belong to AH, then C is the form AB for some B in SL2R. Right? Therefore, what is determinant of C? Determinant of C is determinant of A into determinant of B. Right? But what do I know about them? I know that this is equal to determinant of A is determinant of A and determinant of B is 1, therefore it is determinant of A. So what I have shown is if C belongs to AH, the coset, okay, that implies determinant of C is same as determinant of A. You see that it's something very similar to this case? Yeah, very similar to this. Yeah. So what is that next you would like to ask? Suppose C, let us say D, is GL2R. Okay, then is D is form D belong to AH. So if that be the case, what do I have to do? D must be of the form AB. B must be in SL2R. What is unknown? Unknown is this. Therefore, what should I do? Remember A, B, everything is invertible. Therefore, my B, I can think of this as A inverse D is as B. Right? Multiply this, A times A inverse D will be B. Therefore, so take B equal to A inverse D, and determinant of A, B, I have to check is it equal to 1? Yes. That is because determinant of A inverse and determinant of D. But again, no, you know the determinant is a homomorphism. Determinant of AB is determinant A into determinant B. Okay, multiplicative thing is it. Therefore, I should disable this. Therefore, this is 1 by determinant of A into determinant of D. Therefore, that means determinant of A equal to determinant of D. That we know that. Okay. So what I have shown now, the cosets of SL2R in GL2R is the set, okay, is parameterized by set of all real numbers for each, okay, for each real number. Let us say alpha in R, of course it has to be in R star. Okay, look at this let me call this as C alpha. C alpha equal to set of all A in GL to R, so that determinant of A equal to alpha. You understand that? Therefore, set of cosets are C alpha, where alpha varies over R star. Right? So you can again see these are in some sense parallel. So if you think of the determinant, so look at that. So think of this as GL to R. Okay, then I have this function determinant which goes to R, and it actually goes to R star because 0 is not true. Okay, determinant of any element here is non-zero. Therefore, this will be determinant equal to alpha. This will be determinant equal to beta. This will be determinant equal to gamma. So these are the parallel objects intuitively, and they are all disjoint. Right? Determinant is a function. Therefore, set of function means it takes a unique value. Right? Therefore, something here and something here will have different values, right? They cannot have a common thing. Determinant of this must be beta, then determinant of this must be alpha. If alpha and beta are distinct, they are distinct. Okay? This again shows that cosets are in some sense parallel objects, but most importantly, after definition of cosets, you very rarely look at examples, because most often algebra deals with only finite thing. People don't think of this kind of groups. But even in finite I could do, but I think this is good enough. Okay, let's stop.